place to start is with the nerve impulse. We have some decision from the brain, because it's a skeletal muscle.
Yes.
Decision from the brain sends a nerve impulse down the axon. Axon goes to the motor neuron. Motor neuron at the motor end plate sends a nervous signal to this muscle to contract. The first thing that's going to happen is as that nervous impulse comes down to the synaptic knob, it's going to open up calcium channels in the synaptic knob so calcium can enter into the end of the nerve at the synaptic knob. So those calcium ions help to transport the vesicles carrying ACH, acetylcholine, across the synaptic cleft. So calcium is needed for the exocytosis of the synaptic vesicles filled with acetylcholine to get them across the synaptic cleft to bind with the receptor on the sarcolemma. Because the acetylcholine is a neurotransmitter. Neurotransmitters only work if there's an active receptor, which is one of the problems with like myasthenia gravis. The receptors are blocked, so you have plenty of ACH, but nothing's going on because the receptors are blocked. So you have no muscle contraction.
Yeah.
Yeah. So you have acetylcholine being released across the synaptic cleft, binding with the receptor, and that receptor opens up sodium channels in the sarcolemma. So you have an influx of sodium, some potassium leaving. So what that does is you have the positive and negative charges fluctuating across the sarcolemma because you have an influx of sodium creating a huge positive on the inside, and this is normally minus 90, but now all of a sudden it's positive. So you get positive, negative, positive, negative, positive, negative, action potential spreading across the sarcolemma. That action potential goes down the T-tubules, which are extensions of the sarcolemma. Yeah. So you have action potential spreading down the T-tubule, changing the shape of a protein. That protein changing shape causes release of calcium from the terminal cisternae and the sarcoplasmic reticulum. So the calcium is what's going to bind to the myofilaments here to cause contraction. There's something else I wanted to say with the calcium there.
The troponin and
Yeah, so with the T-tubule and terminal cisternae, this is a triad, because you have two terminal cisternae and one T-tube, so that's called a triad. So the calcium is released. The calcium binds to the troponin on the actin, the thin filament.
Yes.
That troponin causes the tropomyosin to move, opening up the active site on the actin. And then with ATP acting on the myosin, the thick filament, that ATP causes the myosin head to attach to the active site on the actin. As it does that, it goes through the power stroke. The power stroke moves the actin closer and closer together, so you have overlap from Z disc to Z disc, and the myofilaments move closer and closer together. They don't actually get shorter, but the overlap increases. So with each power stroke, the overlap increases. Another ATP comes in, releases the myosin head from the actin, and it starts over. ATP, power stroke, ATP, release. ATP, power stroke, ATP, release. And then the calcium is reabsorbed back into the sarcoplasmic reticulum, waiting for another action potential to come along, starting the process over again. Acetylcholine in the synaptic cleft is a neurotransmitter, and it will keep working until something happens, like the enzyme acetylcholinesterase breaks it down. Once that happens, then the acetylcholine stops working. You don't have any more action potential, and the contraction stops. Myofilaments, myofibril, muscle fiber, sarcolemma, and endomysium.
Okay.
I think that's it.